What do you see?
Sand.
Imagine if we could look so closely, we could see each grain, each particle. You see, there are patterns in everything.
Integrals, infinite series.
I've never seen anything like them. From an Indian.
From the City College of New York. My name is Sabornawise Barrington. Today, welcome to lecture number 12 of ordinary differential equations. Today, Fourier series. So, what is a Fourier series? Well, here's the thinking. Let's say we have any function, even a discontinuous one, like this. Now, here's the thing. What if we want to solve a differential equation with this thing? But, it looks ugly. Well, what's one thing that we love solving differential equations with? Sines and cosines. Especially since taking one gives the derivative of the other, taking the other gives the derivative of one. Of course, with some sign changes. But that's basically the way that these trigonometric functions operate, and we love them for that. So what if we can make one of these fellas right out of sine x and cosine x? So, it's not very successful if we just add one term of sine and cosine. Maybe it would look something like this. But as we add more terms, it slowly starts getting better. Maybe by 5 terms, it's going to start looking like this. Of course, that's a rough estimate. Maybe by 20 terms, it's going to look like this. And at 100 terms, it's going to be indifferentiable from the original function. Like that. So you can see from the white to the red to the green to the blue, we've got increasing levels of precision on our graph. So that's how we make a Fourier series. And doesn't this look awfully like a power series or the Taylor series? Well, yes, but here's the thing. Taylor series and polynomials in general don't work very well with Laplace transforms. And often, if we have like a 20-degree polynomial to get an accurate enough representation of a function, then that's going to take 20 derivatives to reduce to a more digestible form. Meanwhile, ours is going to take at most 4 to repeat. That's easy peasy lemon squeezy. So now, we've got a motivation for why to use Fourier series. It just fits better with the tools that we have at hand. But how do we make a Fourier series? Well, the formulation itself is simple. You just got a sum over some variable n of one series, an cosine nx, plus bn sine nx. So what an and bn are representing are basically how much of each different frequency you want. So you could be like, yes, I would like to order 1 cosine of regular frequency, 1 cosine of double frequency, 2 cosines of triple frequency, 3 cosines of quadruple frequency, and your little order could be represented as this. And in the same vein, we have bn for sine nx. So that's the most necessary stuff we have. And of course, if we want to make any alterations to the to the actual shift, so we want to give it some vertical level, we can add a constant c. All right. So now we've got everything. This is our Fourier series. Hooray! Thank you everybody for watching, and we'll see you in the... Nah, I'm just kidding. You saw it, right?
Yes.
Okay. So, how the heck do we actually know what AN and BN are going
By
to be?
not knowing them.
So, if we have a specific function, like even something simple, like y equals x, which is what we're going to do today, how do we know which function of each frequency to order so that we can actually make our Fourier series work? How can we make something so that by the fifth term, it's going to look like this, and by the 20th term, it's going to look like this, and by the 100th term, it's going to look like an exact replica of the original. How do we make that Fourier series? How do we know what A's and B's to order? Well, that's where a little bit of calculus comes in. So, it all lies in these. Let's say we have sine mx times sine nx, where m and n, they can be anything, but let's assume they're integers for the sake of our sanity. Also because that's the most useful application of them. So assume m and n are integers. Let's say we take the integral sine mx sine nx dx. So how do we know what this is going to become? Well, let's put some limits on the integral first. Let's say from 0 to 1 period, t. So it turns out that if m is equal to n, this gives us t over 2. And if m is not equal to n, we get 0. Now, it's easy enough to prove m equals n, so we'll do that later. But first, let's prove that it's always 0 when m is not equal to n. So let's assume that m is greater than n. Of course, these are just dummy names that we can switch around. So this also applies for the scenario where m is less than n. So all we have to do is say we have sine mx times sine of mx plus n minus mx. All right. So now, what is this actually going to be? Well, it's going to be sine mx cosine n minus mx plus cosine mx sine n minus mx. So we get sine squared mx times cosine n minus mx plus cosine, or if we want to abbreviate it a little bit further, half sine times 2mx sine n minus mx. So that's how we can make our expression a little bit more friendly. But now, how do we actually show that this is going to be equal to 0? So let u be sine x. Then du is equal to cos x dx. Great. So this is just equal to du. So we have 2u squared du, which is just going to be equal to 2 over 3u cubed. So what's that going to be? 2 over 3 sine cubed x. From what to what? From 0 to 2 pi. But here's the thing. Wait a dang second. sine of t is equal to sine of 0. It's just equal to dang 0. So it doesn't even matter what exponent we raise this to. This is just going to be 2/3 of 0 minus 2/3 of 0. And what is that?
0.
Great. All right. Can I venture into experimental territory, or do we want to just stay in things safe?
It's up to you.
Okay,
This
cute.
is called freedom of.
So now let's see if we can use this information, prove it for something higher.
You don't have to erase it.
No, we don't have any more space.
Over there.
Dad, are you kidding?
Why?
I'm trying to do the exact same thing, but with different numbers, okay? Okay. Q. So what happens if we try 3x? Well, we have sine 2x plus x dx. So we have sine x, sine 2x times sine 2x cos x plus cos 2x sine x dx. So what do we get at the end of it? Sine x, sine 2x cos x plus sine squared x cos 2x. Now here's the thing. Cos 2x is equal to 1 minus cosine squared x minus sine squared x. And this is just going to be equal to 1 minus 2 sine squared x. Hence, sine squared x is equal to 1 minus cos 2x over 2. Alright, so now that means that this is just going to be equal to what? Since we've run out of space, I'm going to go over here. We have sine x sine 2x cos x. And then plus sine squared x cos 2x. Okay. Now, this is just going to be half sine squared 2x plus sine squared x. So, this is just going to be 2 sine squared x cos squared x plus sine squared x times cos squared x minus sine squared x. So then we get 3 sine squared x cos squared x minus sine to the 4th x dx. Now, this is too much of an extensive proof for us to do right now, but here's the thing. You can already very easily prove that the integral of sine squared x dx from 0 to 2 pi is equal to pi. This is pretty simple to prove. All you have to do is use the identity of cosine 2x. So then you would agree with me that the same thing would apply had I used sine squared 2x instead. Because essentially all we're doing is just smushing the original function into 1/2 of the space. This whole thing is just going to be pi over 2. Because with half the length comes half the area. So it would make sense, right, for this whole thing to just be 3 pi over 2. Now for this part, we can use another trig identity. Cos 2x is 1 minus 2 sine squared x. So squaring both sides, you get cos squared 2x is 1 minus 4 sine squared x plus 4 sine fourth x. So cos squared 2x minus 1 plus 4 sine squared x divided by 4 is equal to sine to the fourth x. So we get sine squared 2x minus 1 plus 4 sine squared x divided by 4 is what makes up this integral. So then, what the heck is this in the end? Well, it's just 1/4 of this integral. And of course, the rest of this is just full of stuff that we've already done. So that's an exercise left up to you. So using induction, you can prove that this works for sine x, then and sine of n times sine of n times any x. So you get a sine x, sine 1x, sine 2x, sine 3x, sine 4x, and so on and so forth. Then using induction, you can prove that that can be proved for any possible first n. So sine 2x, 3x, for example. At the end of all time, we can prove that sine mx, sine nx from 0 to t is equal to t over 2 if m is equal to n, and 0 if m is not. Same thing if you've got cosine. This is just going to be t over 2 if m is equal to n, and 0 m is not. And finally, if we have the integral of sine mx cosine nx, or vice versa, this is always 0, no matter what. All right, there we go. So now, let's get back to our Fourier series that we had at the beginning. N equals 1 to infinity. So we have, and let's ignore the constant at the end for now. We can ignore that. That's basically just the average value of the function. So we get an, right? We get an times cosine nx plus bn sine nx is equal to f of x. And so, what do we do next? Well, what we have to do is multiply both sides by, well, it depends what you want to find. Do you want to find bn or an? If you want to find bn, you're going to want to multiply both sides by sine. If not, you want to multiply both by cosine. So multiply both sides by sine mx of an sine mx cos nx plus bn sine nx sine mx. And here's what's going to happen. If we take the integral of both sides, then this is going to fade away, since no matter what n is, this is always going to go to 0. And the integral of this is just going to be bm, because this is not zeroed only when n is equal to m, times whatever the result is, which is going to be t over 2. So that means that the integral of f of x sine mx dx times 2 over t is equal to bm. And using the same logic, from 0 to t. 2 over t from 0 to t, f of x cosine mx dx is equal to am. So now, let's try doing an example with this. So let f of x equals x. It's literally the simplest you can have besides a constant function. Let's transform this into a Fourier series. So, what's am going to be? well, if we can make it ak now, that's nicer. The integral from 0 to t times 2 over t, and what's our period right over here? Now, in our case, we're going to be using varying frequencies, so it's just going to be 2 pi divided by the coefficient of x, which is k. So we have 2 over 2 pi over k, which is just 2k over 2 pi, or k over pi. K over pi times this integral of x cosine kx dx. Can we do this integral? Of course we can. It's just IBP. So what's the integral of x cosine kx dx? Well, we let x be u and cosine kx be dv, and then we have x times 1 over k sine kx, and then minus the integral 1 over k sine kx dx. And of course, this whole term is just going to become plus 1 over k squared cosine kx. So now we just have to take this range from 0 to 2 pi over k. And of course, when it's 0, this term is going to go to 0. And this term is going to be what? Well, cosine of 0 is always going to be 1. So it's just 1 over k squared. That's our lower part. Then our upper part, 2 pi over k. Well, we've got sine of 2 pi over here. And sine of 2 pi is obviously 0. So that first term gets 0. Cosine of 2 pi is always going to be 1. But wait a darn second. This is just going to be 1 over k squared again, since this is always 1. So this means this is going to be equal to 0. How did I write 1? So that's not it, though. We've only calculated the series for AK. So that means there are going to be absolutely no cosines. So now we know AK is equal to 0. What's BK? So that's just going to be equal to k over pi times the integral from 0 to 2 pi over k of x sine kx dx. Same thing again with IBP. We get minus 1 over k x cosine kx plus the integral of cosine kx times this 1 over x factor outside dx. And what is this? Well, of course, this is just going to be 1 over k squared sine kx. Great. So now we just take the range 0 to 2 pi over k. This term is always going to get 0 for 2 pi over k. And this term is going to become minus 1 over k times 2 pi over k. And then for this 0 term, everything's going to be zeroed. Literally everything. So that means that our final answer for BK is just minus 2 pi over k squared. Which means that f of x just equal to the sum of BK, which is minus 2 pi over k squared sine kx. So this is the Fourier series for f of x. That's it.